All right. Thank you. I've been told that I have 10 minutes, and as you know, this is really challenging for a researcher when you give the researcher a podium, and it just goes on and on. But I will try to keep it within the 10 minutes. So I thought what I'll do today is, in my outline, maybe in a worldwide health concerns, and all the way up here, I'll just give an introduction to the project in terms of why we're doing it. And given the time limit, I may have to zoom through the results, but I think it's more important to look at in terms of some of the things that we are considering in this project and why it's important. So I think it's no surprise to a lot of people that in terms of worldwide health concern, unclean water is a major issue. Okay, so unclean water and the lack of basic sanitation kill more people every year than AIDS, tuberculosis, malaria combined. So it's actually a major killer. It doesn't sound as sort of a big of a disastrous issue, let's say a major disaster that's happening somewhere, etc., but it's actually a very constant killer everywhere. So I've got, well, something doesn't show up here. I've got two numbers here. I'm sorry that this is so small. I've got 2.1 billion and 2.4 billion. Okay, so 2.1 billion, this number here represents the number of people in the world who are still drinking fecally contaminated water. So fecally contaminated essentially is wastewater or poop, right? So poop contaminated water. And 2.4 billion people still don't have very good sanitation strategies. So in terms of where do they go to the washroom, and after they've done their business, how does the end product contaminate the drinking water? So this is still actually a really big problem in terms of 2.1 billion and 2.4 billion people. So if you think about the world population at about 7 billion and inching towards 8 billion, it's still a significant number. And here's another big number here in terms of 2.2 million people. So this is 2.2 million people that have died, or so in terms of the mortality, the number of mortality or a mortality rate in terms of 2.2 million people that have died due to diarrhea diseases related to unclean water, as well as unclean sort of sanitation and hygiene practices. Okay, and so not surprisingly, a huge percentage of this 2.2 million are those who are immunocompromised, especially young children under the age of 5, who would not survive sort of an incidence of diarrhea attack. Okay. And what leads to this then is in terms of the social economic impact of these diarrhea diseases on people's livelihoods and also on sort of the well-being of the community, of the region, etc. And so hundreds of millions of people have been trapped in a cycle of poverty due to the lack of access to these basic needs. And so I just want to mention that this is 2.2 million in terms of mortality, morbidity, in terms of actually being sick, etc., the rates is actually quite a bit higher in the billion range. Okay. And so one of the technology that we've been looking at here in civil engineering is we targeted something called the biosand filter technology. And this biosand filter technology is actually now starting to be very popular, and it's being used in a lot of low-income communities, in rural communities, in low-income countries. So what this is it is a household point-of-use water treatment system. Okay, so essentially then a lot of rural communities in low-income countries do not have access to a centralized water treatment infrastructure. So they don't have the ability to turn on the tap and out comes the water. Rather, a lot of times what they need or what they rely on is for the women or the children to walk to a water source such as a lake or river to bring the water and back home. So in that pail of water is where you have fecally contaminated water. Right? And so then a biosand filter technology is a household point of use water treatment system. And in a way you can think of it like a Brita filter that you have at home, but it is quite different, but the concept of it is quite similar in that this is a household point of use system. And so this is a Canadian technology that was created in the 1980s or the 1990s. And it has been proven to be very effective in removing biological contaminant. So biological contaminants are things like viruses, bacteria, worms, cysts, etc. So it's been proven to be very effective. Now, why is it that we targeted this biosand filter technology, and why is it that 8 organizations worldwide are starting to notice that maybe household water treatment technology is the way to go? Is because these type of technologies are sustainable, and they're considered an appropriate technology for the local environments. So it is low cost, but more importantly, the materials that are used to build this can be sourced locally. So sand, gravel, etc. So things that you can find everywhere. And the know-how in terms of the skills required to build this is quite simple. So you don't need some very complicated operators to come in and tell you to switch this on and turn that valve off, etc. So then it becomes an appropriate technology for those who don't have a lot of skills and don't have a lot of resources. Now, in terms of how does it work, I don't want to spend too much time on it because I don't have time. But this is a biosand filter. Essentially, it's filled with sand, and then it's there's a black box in here. It's actually quite complicated. It doesn't look very sexy or very sort of complicated from the outside. It's not shiny, but there's a lot of things that is happening inside that actually helps you remove the biological contaminants. It's not just filtration, but it's a biofilter, so there's mechanisms of biological activity inside that actually actively kill the pathogens, right? And so there's a lot of different variations of the biosand filter worldwide. Some people have used concrete, some use plastic containers, etc. And so there's quite a bit of different technologies out there. And so we've worked with this, and we've worked with the organization that disseminates this, the Center for Affordable Water and Sanitation Technology, which is based in Calgary. And then as we're working through this, we realized that there's another problem that we need to address. And this then becomes sort of the meat of the project that I'm going to talk about, and I've already spent 5 minutes. And the meat of the problem is the biosand filter that I've talked about is very good at removing biological contaminants, right? Bacteria and etc. And that's what the aid community or engineers have really focused on in the past. But there's an emerging problem that is facing everyone today, not those in low-income countries, but also in our communities as well, and that is we have chemical contamination of drinking water, right? And so in terms of just a brief explainer, and you probably know this, so you've got agricultural practices, and here, let's say this is some kind of industry, right? And so there's mass application of pesticides on crops, okay? And then there's industry discharges. All of this goes to the rivers and the lakes, and eventually it percolates down into the groundwater. Where we are in Canada and North America, for the most part, we're pretty lucky because when we have dirty drinking water, let's say biologically contaminated or chemically contaminated, we have fancy technology to be able to remove that. Okay, it costs a lot more, but our governments are pretty good, and policy requires that the engineer remove these chemical contaminants. That's pretty good. However, if we sort of look at the other communities where access to these fancy technology is not available, that becomes a huge problem, right? And that becomes what is the focus of our project. And what we saw is through literature search and sort of through contacts and with fellow researchers and colleagues, we're seeing that there's an increase mass agricultural practices in emerging economies. So we call them emerging economies, which used to be called developing countries, but now the term for it is low-income countries or emerging economies. And so, for example, in Southeast Asia, there's mass, actually not just in Southeast Asia, actually everywhere, there's mass application of pesticides. And this mass application of pesticides, for the most part, is unregulated. Regulation is very lax or non-existent in terms of how much you can use. In front of a colleague of mine, Josh Kearns, he's worked in Thailand for quite a bit, and one thing that he noted was a lot of the pesticides that have been banned in North America and in Europe are found on the shelves in communities in Thailand. So actually about 70 to 80% of the banned substances or pesticides are actually being used in other countries, right? And so you can imagine then there's mass application of pesticides, it rains, the chemicals become runoff, goes into the drinking water sources. The chronic exposure, in terms of the dangers of chronic exposure to these chemicals, it causes cancer, nervous disorders, sterility, malformations, and there's a lot of sort of long-term effects of the chronic exposure to these chemicals. If you sort of perform a literature review on the evidence of chronic exposure of communities to different chemicals, it's hard to come by in terms of epidemiological studies in developing countries or low-income countries. But Ghana, Jordan, Thailand, if you just do a search, there's actually a lot of incidents of a presence of pesticides in breast milk. In fact, this one study here in Thailand, they looked at a indigenous tribe, the Hmong people, in one part of Thailand where they have been exposed to, or they're surrounded by a very agriculturally intensive environment. And they sampled the breast milk of the women, of the mothers, and they found that the presence of DDT in the breast milk is 20 times higher than that recommended by World Health Organization. So which means that the infants or the children who are feeding on the breast milk have been exposed to a acceptable daily intake value 20 times that which is acceptable. And all of that is because there's all of this mass agricultural practices, lax regulation, etc., that is happening, right? And so our research question then is we want to address this chemical contamination in drinking water, particularly in resource-limited environments. Okay? So the first research question that we have is, we've been dealing with the biosand filter. Well, how good is the existing biosand filter in removing chemical contaminants? That was the first question. If it had been removing chemical contaminants really well, then we're good, right? Okay. The second question is, well, if question one shows that the biosand filter doesn't work, then how else can we modify the biosand filter so that we can actually remove the contaminants? Now, the challenge in this, and the context of it is very different than the communities, the types of technologies that we use here in Canada, is that the technology that we're going to apply with our biosand filter has to be an appropriate, affordable, and sustainable at a household level. So we're not looking for sort of aid organizations to come in with a fancy Brita filter that says, here, use this, it'll work really well. But unfortunately, research has shown that these kind of practices are not sustainable. Okay, so that's really the challenge for us. All right, so here we've got a few methods slides. So to address question number one in terms of the biosand filter, what we've chosen is we've chosen a representative pesticide to use in the lab. And so we've chosen atrazine. Atrazine is a herbicide that is used for agricultural practices, for example, in soybean, sorghum, corn, pineapple, etc. So it's a widely used herbicide for grains. And so we've looked at it in different concentration range of 10, 100, and 1,000 parts per billion. Now here, and actually, I just want to mention that this is a really challenging part for our researchers here at BCIT. So this is a collaborative project with Department of Chemistry, Dr. Kevin Salisbury, who is also part of this project. Unfortunately, he's not here today because he's at a conference. But the concentration range of 10, 100, and 1,000 ppb, parts per billion, are very, very small. It's actually quite difficult in terms of coming up with protocols or analysis protocols to be able to investigate this. And this is where Kevin Salisbury and his students spent a lot of time in terms of coming up with analytical methods to develop that. When we did a research, initial literature survey, there has been a sort of a lot of different research that looks at how sand filter is able to remove contaminants, but all of those concentrations are at a much higher concentration. So in a parts per million range, as opposed to parts per billion. And so in many sense, one of the challenges with research is what you find in the literature is not necessarily relevant to practice, because the ranges that are encountered in the research is very different than what we're seeing in terms of environmental concentrations. So we were dialing it down to actually quite low values. The water matrix that we used was, we used Gishon Creek water to represent actually a real water as opposed to deionized water. But we also used deionized water that is blended with municipal waste. We performed a few other things. There's tracer analysis to determine the flow profile inside the filter. We performed microbiological testing and so on. So here I just want to show you in terms of, these are the biosand filters that we have in the lab. So this is actually what a biosand filter looks like in a household level, and so we have quite a few of them. And because of the logistics of pouring a lot of chemical contaminants in here and having a lot of waste products out, we decided to build a skilled version of the biosand filter. The skilled version of the biosand filter. And this is what it looks like. So it's about 1 meter high and about 10 centimeter in diameter. And so we did a few things. We performed a trace analysis of the filter, right? And then what we did also was we added some water with spike with atrazine solution into this filter. And there were still other sort of operating parameters that we varied and looked a little bit more in detail, which I won't go into in detail. All right, so the results for this research question number 1 is, in terms of tracer analysis and the flow profile, we found that flow inside this filter behaves like a plug, which is really important in terms of understanding how contaminants are in contact with sand, etc., and how much time it is and how uniform it is. In terms of microbiological testing, in terms of the removal of total coliform and E. coli, it's in a range of 90 to 97%. Oh, this is only research question number 1. Right, and so that it shows that our filter works really well. Okay, now the interesting result is in terms of atrazine removal. Okay, so in terms of the different parameters that we have, the different filters that we have, the average removal is between 1 and 7%. In terms of atrazine removal, that is not okay. So that tells us that the biosand filter doesn't do much in terms of chemical contaminant removal. Okay, so we've answered that. All right, so the second research question is then, right, so what can we do to modify this biosand filter to remove chemical contaminants? Remembering that it has to be an appropriate technology available, appropriate technology in a low-income, resource-limited environment. So what we looked at a few things, but then we zeroed in on something called a biochar. So biochar, essentially, it's kind of like your charcoal, right? And so charcoal, actually, we don't use a lot of it except for our barbecues, but in a lot of different parts of the world, it's actually sort of their main source of fuel for heating and for cooking as well. And so it's actually quite abundant everywhere, okay? And the precursor for a biochar is biomass. So essentially how you produce biochar is with agricultural residues. It could be wood, but it could be manure. It could be, I don't know, rice straws, bamboos, anything that is left over, so agricultural residual. And biomass is converted to biochar at elevated temperatures. So essentially then what they do is they would actually burn it in the absence of oxygen, and it creates some kind of properties on this char that is very amenable for absorption of chemical contaminants. So it is kind of like the activated carbon in your Brita filter, but without the activation step. So it's not as good, but it might work just as well, okay? So we consider this to be an appropriate technology because it is low cost, right? Agricultural residues everywhere. Okay, it can be sourced locally, right? You can find it locally, and more importantly, you have the knowledge or the know-how in the local communities to do that. So I mentioned that a lot of people actually use charcoal for fuel and heating, and so then in terms of biochar production, there's different methods. There's kilns, gasifier systems, and then their earth mount system, right? And so then there's local community to do that. Okay, so what we did was we had to buy some biochar. Okay, so the first biochar that we found was from a Canadian producer, and they've been producing biochar, so we got some of that. And then the second biochar, I have a contact in Indonesia where this person went to a wet market in Indonesia and just bought a charcoal that they bought from the wet market. Okay, so something that is locally available. And so we analyzed it in terms of what the differences are between the two. I'm going to skip all of this in terms of what we did in our experiments, but we did a lot. And I just want to get to the meat of the results just very quickly. So if you remember, between biochar A and biochar B, keep in mind that biochar B was what we found from Indonesia, just locally, compared to what was produced in Canada, biochar A. On the y-axis here, it's percent of initial atrazine remaining versus days. So this was our lab-scaled absorption test, and we found that biochar B, what we found in Indonesia, performed really well in removing atrazine. So that's one thing. And we investigated a few things in terms of how particle size of the biochar behaved and in terms of its removal ability, etc. And we found that smaller particle size was actually better than bigger particle size, which is no surprise to us. And we also found that for the biochar, it is not able to remove atrazine as well as some of the other chemical contaminants, such as the polycyclic aromatic hydrocarbon. So here's the main result. Okay, in terms of a filtration experiment, okay, we compare our biochar filter to a granular activated carbon filter, which is a GAC carbon filter is what we would have here in Canada in terms of a good filter, right? And so we compared our biochar filter to this GAC filter. We found that for atrazine, of course, the GAC filter is able to remove 100%, but the biochar filter is able to remove between 37 to 97%. In terms of naphthalene, it's able to remove 49 to 93%, and then 100% removal of phenanthrene and anthracene. And sort of the lower range of this, 37% or 49%, was actually after 1 month of filtration. So it started out in terms of percent removal versus volume filtered. It started out actually with very good removal, and then it declined over time. Okay. All right. So conclusions. See, there's this is the problem with giving the researcher the podium. All right. So the summary is the biosand filter is not very good at removing the chemical contaminant, but we think we found something that works, but we have a lot of work still to be done in the lab to figure out in terms of how to bring it from a lab scale to a field scale and to have it actually put in place in practice. So there's quite a few more things to do. I just want to acknowledge that this project was funded by the Discovery Parks Fund here at BCIT, and we just want to really acknowledge our students who've worked on this project, civil engineering and chemistry. And also we had support from SFU 4D Lab as well. I don't have my students with me, but here they are. And this is only a few of them. I wish I have more pictures of them, but there they are. Thank you for your patience, and I'm sorry.